So we're going to look in this video at how to solve higher order equations. All of the ODE solution techniques that we've looked at so far can only solve first order ODEs, and by first order I mean the highest derivative is a first derivative. How often do we see first order ordinary differential equations in engineering? Well, not very often. It does happen sometimes, but nearly everything that we look at are higher than first order. So, for example, the equations that describe a pitching and plunging flat plate, for example, some airfoil, is this rather complex vector equation here where Q is our unknown. It's a vector h and alpha, where h is the displacement and alpha is an angle. We can see that we have a second derivative term there, a first derivative term and a linear term there, and the A, B, D, E and F are all matrices. So this is a matrix equation. It's moderately complex, and it describes what happens, for example, in applications in aeroelasticity, where you have a wing that is twisting and also going up and down. Another example is a damped non-linear oscillator. So, for example, something like a shock absorber. The motion of that can be described by the equation x double dot is equal to negative dx dot minus kx, where d is a damping coefficient and k is a spring constant. Both d and k are greater than 0. If they're both constants, then an analytic solution exists of the form that x is equal to some constant times e to the minus 1/2 dt times cos omega t, where omega is equal to the square root of the spring constant. However, what do we do if both the damping coefficient or the spring coefficient are actually functions of both x and x dot? There is no analytic solution. How do we handle the second time derivative, this x double dot here? That's the thing that we're going to be looking at here. So in the most general case, we're going to want to solve an equation that looks like the following: that the nth derivative of our unknown function y is equal to some function of x, here we're doing things as a function of x, of the solution itself, and of all of the derivatives of the solution. So that's the general equation we're going to want to solve. The basic idea here is to introduce a hierarchy of variables, y1, y2, y3, etc., up to yn, where we define the different y's according to the following. First of all, we let our unknown y equal y1. So once we've found y1, we know that we've actually found the thing that we're trying to look for, and that thing here is this y. We then say, okay, we want to let dy dx, which obviously from the above equation is also equal to dy1 dx, be equal to y2. So we're defining y2 using that equation there. So we're introducing a new variable that's equal to the first derivative of our solution. We then say that the second derivative of y, obviously that's going to be equal to dy2 dx. We're going to let that equal a new variable, y3. So we've defined another ODE. dy2 dx is equal to y3. And we can go on. So the third derivative is equal to dy3 dx, equal to a new variable, y4, until finally we get to the bottom, and we can see that the nth derivative of y is going to be equal to d by dx of yn, where that's a new variable that we've just introduced, and that is going to be equal to the right-hand side of the original equation, but now we replace all of these derivative terms with these terms that we've calculated here. So that's the set of equations that we've introduced. So taking the essential definitions from the previous page, just to make it a little bit clearer, we define y as being equal to y1. That's not an ODE, that's just a definition. And our set of ODEs then is the remainder of these equations. dy1 dx is y2, dy2 dx is y3, dy3 dx is y4, etc. up to dyn dx is equal to a function of all of the other variables that we've introduced. And that depends on what was on the original right-hand side of our ODE. So that gives that first order set of ODEs there. We can write the unknowns as a vector. Y is equal to y1, y2, etc. We can transpose that to turn it into a column vector. And then we can write our system as dy dx is equal to f of x and y, where f now is a vector right-hand side which comprises of that, etc., all the way up to that. And these can be solved, for example, by using Euler's method. So going back, we would do it equation by equation. So y1 at I plus 1 is equal to y1i plus h y2i. y2 I plus 1 is equal to y2i plus h times y3i, etc., down to the very last equation here. That's just equal to yi plus 1, where y now is the vector, is equal to yi plus h times the right-hand side vector function f. This vector notation here is going to be useful when we're thinking about coding this problem up in MATLAB. Let's quickly work a concrete example to make sure that we can all figure out how this works. So let's look at a pretty complex ordinary differential equation. It's a third order equation because we have a third derivative term here. U d cubed u dx cubed plus d squared u dx squared plus sine of du dx plus u squared is equal to g of x. So the first thing is we say, okay, our unknown solution is u. Let's let that equal y1. So when we calculate y1, we know that's the same thing as u. Then du dx is simply equal to dy1 dx, which is equal to y2. So this is a definition of y2, but it's also one of our ordinary differential equations, our first order equations. We then say that d squared u dx squared is just equal to the first derivative of this entire expression here, is equal to dy2 dx, and we're going to let that equal y3. It's a new variable. So here is our second ODE. D cubed u dx cubed is simply equal to dy3 dx. That's not actually an ODE yet. We need to calculate the last ODE from this expression here. So let's substitute dy cubed dx for this, dy2 dx, sorry, y3 for that, y2 for that. And we substitute those in. We end up with the ODE that equals y1 dy3 dx plus y3 plus sine y2 plus y1 squared equals g of x. If we shift all of these things to the right hand side and divide by y1, we end up with, I guess, what you might call the canonical form of our first order ordinary differential equation. That's dy3 dx is equal to g of x on y1 minus y3 on y1 minus sine of y2 on y1 minus y1. Of course, we need the other ODEs that we calculated earlier. Those are those two that I've left there in the green boxes. So we need to include dy1 dx equals y2 and dy2 dx is equal to y3. So this equation here, this equation here, this equation here completes our set of three first order ODEs.